Hi everyone, and today I'll be touching on my latest research. It's titled Learning Fast and Slow. So before that, actually, I came up with this idea sometime in NeurIPS 2022. So I was looking at the reinforcement learning posters. I attended the memory workshop, and basically I found that actually a lot of the modern AI systems only focus on the neural network aspect of things. And I feel like this only encompasses one specific kind of learning, like more like procedural learning. And I was thinking, what if we could also incorporate some form of memory inside this so that we can learn faster from memory, and we can also utilize the neural networks generalization ability and also learn from there as well. So I had this train of thought whereby you could have two learning systems that complement each other. One is a like fast kind of inference, like a neural network, and the other is like a slow kind of system whereby you can use this slow system, otherwise known as the memory retrieval and storage system, in order to do future planning. Okay, so why exactly each of these systems are geared towards each function, I will explain later. So there's some insights that I got from some experiments, and that's why this system was structured as such. So this whole system took about 1 month to formulate, and it achieved pretty impressive initial results already in a grid world-like environment, and it outperforms actor-critic methods like the proximal policy optimization or trust region policy optimization or PPO or TRPO. So there's some promise in this method. I'm still actually doing more experiments on it. And I'm actually quite happy to share with you this idea. The key thing of learning fast and slow is basically two things. One is the goal directedness, and the second is the memory base. So let's begin. So this one, if you have seen my other video called the reinforcement learning fast and slow, it is like about 60 to 70% similar, but there's more experiments now and more follow-up. Right. So what exactly is the aim of this work? Right. The aim is actually to mimic how humans learn very quickly. So if you look at like modern RL architectures, they can actually solve like Atari games, and they solve it at a rate that is actually very, very slow. Like it takes about 1 million or basically more than 1 million frames, right? Sometimes even going up to giga, G is, I think it's Jillian. Yeah. So basically, it goes way more than what a normal human would take. Like the computer systems take about 3 days to do like reasonably well to match human performance in some Atari games, while humans only need 2 days. Sorry, 2 hours. So this is really one of the key reasons why I was looking into this, because I feel like modern ways of learning, like the reinforcement learning algorithms, are just too slow. And in order to adapt to like a changing environment, like such as real life, you have different, like whenever you drive a car out in the road, you don't see the same cars, you don't see like the same road situation. You actually have to adapt, and you have to get used to whatever environment presents to you and get to your destination. So how can humans do it so well while computer systems take so long to learn? So that's one of the things that I like to seek insight from biology, neuroscience, or psychology, and try to model it out in a system that can do well in a changing environment. So I term this kind of agent a fast and adaptable agent. Right. And another thing is I do not seek to replicate the brain, because I feel like the brain may have some incompetent parts because it is still fashioned somewhat by evolution, which can take very long to make a change. So if we can do something that is more efficient than what the brain is currently doing, like for example, the memory system, we don't have to follow exactly what the memory system is in the brain, which is something that is very quite foggy and then prone to recall errors. Stuff like this, we may not need to model. We can just use the more efficient like computer kind of memory. Of course, there's pros and cons. We can discuss that later. So this is the key background behind the work. So what exactly is the traditional reinforcement learning? So I just put this slide here just to illustrate for those who don't really know what's reinforcement learning. It typically involves an agent interacting with an environment. And what happens is that the agent will get like a state from the environment. Like for example, an observation. Like if you drive a car, it will be the video frame of like what you are looking at. And then the agent will then take an action. Like for example, should I accelerate? Should I brake? Should I move left or move right? That's the action. And then you take the action, go to the environment, and then you get your next video frame, for example. And then you keep doing that until you reach like your destination. So in cases like you get your destination, you get like maybe reward 1 at your destination and reward 0 otherwise. Something like that is like reinforcement learning. So what I've just described is actually like a sparse kind of reward where you get reward 1 at goal state and 0 otherwise. In most cases, the reward in reinforcement learning is actually more dense. Like you get rewards at every single time step in order to encourage the agent like to take certain actions. Like for example, moving forward, whenever every like distance that you move forward, you reward the agent based on the distance moved forward. That's like for Mujoko environments where you have a robot walking. Those will enable the agent to learn faster. Okay, for this kind of sparse reward problems, reinforcement learning actually has difficulty learning. So this sparse reward situation is actually what led to this work. Okay, because I think that the reason why reinforcement learning agents don't learn well from sparse rewards is because using rewards to model like a particular objective you want to achieve may be actually a very slow way of learning. And perhaps we can use something else, something like a goal-directed means of learning, right? Okay, so let's move on to the next part. All right, so this is just a simple thought experiment. Maybe I would like to just invite you all to just take part. Okay, so you probably have seen this before, but let's just try this again. So if let's say we have like 2 doors, all right, for example, one door would lead to your office and another door wouldn't, all right? So if you are now standing in front of the 2 doors, how will you choose which door to open to go to your office? All right, so maybe I just ask, who here thinks that we calculate an internal value function for each door? Like maybe this door will give me an expected like reward of maybe 3, and this door gives me expected reward of 1. Therefore, I choose this door. Anyone thinks that we use value functions to calculate like which door to open?
No.
No, okay. Or the second one is, do you recall like a particular sequence of actions or some memory, and then you choose the door that corresponds to that sequence of memory that eventually like maybe leads you to your office?
Yeah,
Okay.
I think the memory one.
The memory, right? So this simple thought experiment, Evan, you agree that we think by memory most of the time? Or rather make decisions by memory?
Yeah.
Yeah. Okay, thanks for... All right, so this is one illustration that value functions alone may be not insufficient to model your decision-making process. Because one thing for value functions is that you compress everything down to maybe a scalar value. And this scalar value will need to contain all the information that will like give you the like the value of the future states and so on. It really takes very long to learn this value function. And this value function can keep changing if your goal changes. So this is actually quite inefficient, and more often than not, using memory would actually be a more efficient way of learning. Because if you already memorize like certain sequence of like images that you see to your office, you can like prime yourself to, okay, this matches with my memory, hence this should be correct. Yeah, it's actually a more approximate, okay, but it's actually very effective. Okay, so I mean, we don't really get lost that easily if you actually memorize landmarks. Okay, so actually I also did this experiment on myself. So you all know, like for example, in car parks, right? Car parks, they all like kind of look the same all around the car park. Let's say if I don't purposely look at like what letter the car park is, like K, column M, or what color. If I don't purposely remember that, the chance of me getting lost and unable to find a car is actually quite high. All right, so actually I need to like prime myself. Okay, this is pillar number K, pillar letter K, orange color. Then you try to remember exactly that landmark, and you can like navigate back there again. So yeah, this is just one example of like how memory actually helps with navigation. Yeah. Okay, any questions so far for this? Okay, let's move on. So this is the next part on how to model the world. So this is new. Okay, so this part here is actually an experiment that I did in order to see whether or not the next state prediction. Okay, next state prediction means like this. Suppose I have this like video, or rather an image that I see right now. And then like if I do a certain action, like if I throw a ball, where should the ball be? Okay, maybe I ask all of your first. Okay, do you think we can predict the next state of our lives accurately? Okay, so this is a thought experiment. Someone throws you a ball right now. Okay, imagine like someone throws you a softball or basketball, right? You see the first 1 second of the trajectory of the ball. Okay, and then you shut your eyes. Can you, without even looking at where the ball is, can you grab the ball when it comes to you? Okay, maybe we just like ask do you think it's possible? You only see the first 1 second of the trajectory. Can you predict where the ball will be so that you can catch it without even opening your eyes?
I think it's quite hard unless you are like quite that lot of experience.
Yeah, thanks, William. How about Evan or Zeri? Do you think you'll be able to catch the ball? Okay, so it's okay. Yeah, you can just let me know through the chat or anything. But the thing is, it's actually quite hard to make next state predictions right now, because the fact is our real life consists of a lot of things we cannot predict very accurately. Like for example, how the leaves blow on the tree. Those kind of things are not exactly the kind that are easy to model. So I just did a very simple experiment to just illustrate this point, that to model exactly what the next state is in our imagination can be quite difficult. And this experiment is like this. You have a grid world. I use grid world because the environment I use later is also a grid world. So you have a random start state and random end state. And what I do is, for the first 50 epochs here, I prioritize like the first move. So the first move will be like towards the x-axis. Initially, this is the x-axis. And then the next 50 epochs, you'll prioritize moves towards the y-axis. So this is the x-axis move, and this is the y-axis move. So the actions that you can choose are up, down, left, right, and don't move. All right. And the next state action will be like, if you choose the x-axis action, the next state will be like at this point C. If not, it will be at this point D. All right. So the first experiment here is just to predict actions, like basically predict the next action, up, down, left, right, or don't move. So you can see like for the first part here, the next action prediction in a 10 by 10 grid, it already takes about 10 epochs, okay, to predict the next action like accurately, about 0.99. Okay, once I do like a shock simulating an environment change, all right, basically swapping from the x-axis to the y-axis, you can see that it takes maybe about 5 epochs. So there's some learning there, okay, because you take a fewer number of episodes to adjust. Okay? But you can see that it still takes a while in order to get your prediction accurately. And this is just with 1,000 samples, and then I keep running through like that. So that is just for action prediction. Like you predict what action you should do, like given okay, so the state over here is just the XY coordinate of the start goal. Okay, plus the XY coordinate of your goal. So maybe you can just call it X prime, Y prime. So the input space is just like 4 coordinates. It's very simple. I didn't use vision at all because it's just a proof of concept to show how difficult the prediction problem is. Predicting a state is even worse than predicting action. You think that, oh, you just need 10 epochs. That's actually not too bad, right? That actually looks like a huge number. But if you look at the number of epochs it takes to predict the next state accurately, you see that it takes close to 200 for like just for the 10 by 10, right? And then maybe it takes about, I don't know, 150 in order to converge again after the change. So over here, I change it at 200. The x-axis and y-axis prediction, I change it at 200 because it just takes that long to converge for the 10 by 10. So I give it some time to converge. So you can see that if we want to do a next state prediction, and this is done using a neural network, right? It's just using 2 MLP layers of, I believe, 128 nodes. And then after that, we just do an output of softmax to choose the next state or choose the next action. Yeah, you can see that choosing the next state is a difficult problem because it just takes so much more time to learn the next state. All right, so this is an illustration of the problem. All right, if we want to use neural networks to predict the next state, it is very slow to learn. And yeah, I hope this point is clear. Because a lot of recent works right now in reinforcement learning are trying to use this thing called world models. And by world models, what exactly is trying to do is to predict the next state of the world using a neural network. And as I said earlier, the next state prediction really takes a long time to predict, like almost 10 times as much as the next action prediction. So this kind of works, like for example, mu0 not just predicts the policy and the value function, right? They do a policy value function, and also they do a transition function, basically to predict the transition probabilities of a Markov decision process. Okay, so this kind of thing is done in mu0, which is the extension of AlphaZero or AlphaGo, the AI that beat Lee Sedol in the game of Go, the black and white stones one. So we also have another one called Dreamer. So Dreamer V2, V3 does a similar kind of prediction that is in latent space. So the prediction of Dreamer V2, V3 is in latent space. And we are trying to predict the next state of the latent space given the current state and the action. So these models have superhuman performance, yes. But what they didn't really look into is how long do these models take to train? Chances are they may take days or weeks to learn this Markov decision process. So what is a Markov decision process? It looks something like this. You have a few states. Each state has a certain transition probability to the next state. Like here's, if you take the same action, you transit half the time you go to state 3, half the time to state 2, and state 2 you transit, you go state 1, state 3 you go to state 2. So this is a Markov decision process. And in order to learn it, okay, you can use like world modeling. But as what I shown in the previous slide, learning to predict the next state of the world can actually take a long time, a much longer time than learning how to predict the next action. So I personally like the idea of world models, but I do think that it is impractical to model the world. Okay, so a lot of people might disagree with me, but based on empirical studies, okay, modeling the world is really a difficult thing, right? And not just the point that the amount of states that you need to model is like infinite, possibly infinite or unbounded. Okay, this is actually a practical problem because if you have so many different new states that you can go into, how can you model the world accurately, right? If you can go to 1 million different states, you need to sample each of these million states at least one time in order to model the world properly. All right, that's one problem. Okay, that's a problem that self-driving cars need to solve, because self-driving cars, there's so many different things that can occur out in the real world. Like there's one study that talked about like tail cases of like self-driving cars. For example, like most of the time you see normal road conditions. What if sometimes you see roadworks? How can the car be modeled correctly so that you can avoid the roadworks? What if someone puts a snowman on the road? So that's a very, very low probability, but that can possibly happen. And if we like try to use these world models, we kind of need to model the entire Markov decision process and make it very, very accurate. You will take forever to learn. You will take a long time to learn. Another potential problem of this kind of world models is that you want to model the transition probability. And to model a transition probability, you actually need to sample many, many times in order to learn it accurately. So all these are actually inefficiencies of world modeling. And so the proposed method that I have will do away with modeling this kind of Markov decision process probabilities. And instead, we can turn to memory systems to do an approximate modeling. Okay, any questions so far on this? Okay, so let's move on to this idea.
Sorry, I have one comment.
Oh, yes.
So this is the deterministic process, right?
You can also model stochastic processes.
Okay.
Yeah, but this example here is stochastic.
I think I forgot. Maybe do you mind to describe that part again, or
Uh,
maybe later?
Sorry, which part? You mean the using memory to model, is it?
Model stochastic processes.
Oh yeah, sure. It's in the next slide actually.
Okay.
It's here. Yeah. So one thing that I believe the modern reinforcement learning methods kind of have difficulty in is actually modeling this world model accurately. And that is because we are kind of obsessed with optimality. Reinforcement learning came about because people wanted to win in games, Okay, that's one of the reasons, right? We want to do well in like chess, Go. So these kind of games are very optimal. Like you make one wrong move and that's it. Right? That's why humans actually do quite badly at it, because we also are not very good at computing optimality. So my position is that humans are not optimal. Okay, what instead we do is we will try to achieve our goals within whatever information that's available to us, right? So there's some benefits to that. For one, you don't have to model the whole world, all right? You only need to model the part of the world that you are currently experiencing. Okay, let's put this in a practical example. If you are living in Singapore, do you need to model how life would be in the United States? Okay, not really, right? Because it doesn't concern your daily life, right? But this kind of systems that you have to do the world model for like Atari games and stuff, they try to model the entire world. Okay, why? All right. Okay, anyone can answer this. Why do you think in Atari games, to maximize your reward, why must you model the entire world? All right. So, well, I mean, if you have an answer, you can say it out right now. If not, I will just like try to illustrate the points using some pictures. All right. So suppose you have a certain game state here, and you can take action A or action B. All right. Action A, you can go through a series of moves, and then maybe you get a value of 2. Action B, you go through a series of moves, you get a value of 1. All right. So in order to get the maximum possible score, like 2, you kind of need to look at all the different actions, right? You need to make sure that you explore fully all these actions in order to make sure you don't miss a potential move that can get you a higher score. So if you want to achieve optimality, you kind of need to explore everything, or you need to have a smart way to explore, but eventually you still need to explore everything, because there's a chance that the path that you didn't explore might be the optimal path, right? What are some of the potential disadvantages of optimality, right? For one, you need a lot of samples. You need a lot of time to gather experience, because if you miss out certain experiences like that, or sorry, you miss out certain experiences like this A over here, you might actually miss out on the optimal solution. So in order to achieve optimality, you are forced to look at every single thing. You're forced to model the entire Markov decision process. But if you are not concerned about optimality, you can just model a small part of the Markov decision process, and your agent can still work. It's just not guaranteed to be optimal, but it can still do like a pretty good job. All right. We don't really have to achieve optimality for most real life tasks. All right. Like navigation, you go one step backwards. Does it mean that you lose the game? Not really, right? You can still continue forward and you can still reach the end goal, right? But most of the benchmarks in reinforcement learning are like those kind that you do one wrong move, that's it already. Yeah, then that's why we have this need, all right, to model optimality in the reinforcement learning benchmarks, because of the way the benchmarks are set. All right, if we don't set this kind of optimal based benchmarks, actually you can learn much faster. All right. So that's one of the key insights. So that's my first point. You don't have to model the whole Markov decision process. All right, especially for processes which involve an infinite amount of states. It's just impractical to model everything. Right? You have the intractability problem of your probability, because there's just infinitely many states you can go to. Right? This is the second point actually. There's no need to model the probability of transition. Right? As long as you have some form of memory bank, you can sample from that memory bank. Again, this is Zuri's point, right? How do we model stochastic events? Okay. Fundamentally, my belief is that the world is deterministic. Okay, but a lot of people might disagree with that, like quantum mechanics and stuff is random, right? Random on the surface, but deep down, maybe it's deterministic. All right, who knows? Okay, but for most practical real life cases, all right, you don't have this case whereby, like, if I want to move forward, 90% of the time I move forward, and 10% of the time I take a random action. All right, that's what happens in some grid walls. You have a stochastic element whereby a certain percentage of the time you take a random action, which just doesn't really make sense in the real world. So if we don't need to model this kind of arbitrary stuff, the reason why like they added stochastic actions inside like the environment, the rationale was to make it more challenging. But actually the real reason is to hide the fact, this is my own words, by the way. The real reason is to hide the fact that this entire modeling process takes so long. So if you add in like stochastic actions, you are forced to model the entire Markov decision process. And so you can then justify, oh, my method actually works, although it takes long, but the next best method also cannot do as well. Yeah, so stochastic actions can actually help to boost that point and like try to ignore the fact that like you take a long time to learn the world, all right? But if we don't have to model probability, if the actions are deterministic, as in most of the cases in real life, like you do a certain action, you don't get a chance that you don't do the action. You will most probably be able to do the action and do, yep. So Terry has a comment. In quantum mechanics, the evolution of quantum system is actually deterministic. It's the outcome of measurement that is probabilistic. Yes, actually that's a good point. All right. The way physics works might be deterministic in the entire system itself. It's just that we are not able to distill out what exactly is this deterministic relation. Yeah. So I'm not an expert in quantum physics, but the thing is, I do not think there's a need to model like stochastic transitions most of the time, right? Some use cases, yes, like gambling games. We force ourselves to be stochastic, but most real life cases, you don't have to model that, all right? You don't have to model the full Markov decision process, all right? And the alternative to using like a neural network for world modeling and use memory as a way to do world modeling is that you can just only remember the transitions you experience, and then you can then retrieve it. All right, so this is just an example. So let's say we have action A leads to state 2, action B leads to state 3. This is something different from the previous slide. Previous slide was stochastic. This is deterministic. You take a certain action and you go to the next state. Okay, but of course, if you want to make it stochastic, you can take the same action A here and then you can go to another state like that. You can model it like that as well. All right, but what we can do is based on our experience transitions, we can then like given a certain start state, like currently I'm in state 1. Then let's say I take the action A. I can then ask my model, what will be my next state? So what I can do is I can use like some form of attention mechanism, to match to the nearest key. Right? So you have a query. Your query, okay, this is actually similar to a transformer. Your query is the current state itself. So the query will be 1. All right. Then we ask the memory bank, the key value pair. All right. Which memories correspond to the query 1. All right. And then they will give you this 2 over here. Next state 2, next state 3, and action A, action B. Okay, then knowing that I have done action A, I can then filter out this memory bank. So actually I can have the action be another query. So your query can be action A. So it can be a dual like key value pair here. So although it's not really shown over here, the way I implemented it is this is actually the key, the sub key, and this is the sub value. All right. So the first level value is here. It's like a nested dictionary. And then the sub level value is this one. Like you use this action as the key and this as the value. And then you can then model, like if we ask this will be action A, and then you can retrieve the next state. So I know when I'm in state 1, performing action A, I can go to state 2. So this is exactly like how we would model this MDP here. Okay, but there's a difference. All right. If you have not experienced this, like let's say action C gives you to state 5, if let's say you have like state 5, action F gives you state 6 or something like that. Yeah, you haven't experienced all this. Okay, in this memory construct, okay, you don't have to model all this. All right. So what you lose out is you lose out on optimality. What you gain the speed of learning. Okay, how fast can this memory system learn? It actually learns in 0.1 time. All right. Because the moment you experience a transition, you can just add it to your memory bank. It learns very fast. All right. Compared to a neural network. Neural network is quite long to learn. right? So this is next slide. I just illustrate the point of like traditional approaches in reinforcement learning, trying to learn a world model versus using this memory system. So the traditional neural network system, like use transformers or use CNNs, or whatever network, is fast to infer because you just pass through the network once and you straight away will get your answer. All right. But for memory, what you need to do is you need to actually query the memory bank, and then you need to cater for any conflicts. Then you need to resolve those conflicts. And sometimes if there's like a billion like things in the table, you might actually take a while to infer, right? But fortunately, this actually can be solved if we use like some approximate techniques to query the memory. Like for example, you take the L2 distance and then you just choose those with the smallest L2 distance. It could probably be implemented in parallel as well. So actually, this is an idea that I have. I haven't implemented it. So this is how I think memory system actually works, like perhaps in the brain. So you have a certain query you want, and then your query will then go through some grand like schema, and then this will actually be pumped out to all your different like memory nodes. So this is actually a decentralized model. Okay, the way I implemented was a centralized model, but let's say you have different, like this is your memory 1, memory 2, and memory 3, and so on. So based on how similar your memory is, what could happen is that perhaps the memories that are more similar to query gets routed back first. So we could just implement a delay that kind of delays the sending back based on how similar the memory is. The more similar, the faster you send back. And then once you send back the memory, all right, you can then do this thing called, sorry. So this is actually a new idea that I have. It's not in my paper, but if you can send back this memory, and then after that you do this thing called the lateral inhibition, you can actually get the closest memory send back first. Yeah, so you can actually do this actually in more or less like O1 times, very, very similar to like a neural network kind of. It might even be as fast as a neural network because you just send out the query, and then things that are similar to you will get pumped back first, and then after that you stop accepting the receive request. It's actually massively parallel. So I would say that there's a possibility that this memory technique, if you implement it correctly, it could be also fast. All right. So I put here slow because the DeepMind paper for the large-scale retrieval of reinforcement learning, they actually use the L2 distance in order to choose the memory and probably also rank them. So that actually, if you do that, you still need to sort them. It might still take a while. But if we do this parallel method, okay, actually it can be as fast as a neural network. Okay, I'm not sure if you can understand this. Yeah, Terry, do you understand what I was saying here? Okay, it's all right.
Yeah. I think we discussed this before.
Okay, yeah. So this one is one of the things that the memory system could actually help with. All right. So the next thing is neural networks are actually not very good for learning a particular key value pair. So like if let's say you query a key here and you outcome a value, the moment you change certain weights, all right, you change certain weights here for another key value pair, you might actually end up with a memory that is corrupted because you learn a new key value pair. Your earlier key value pair might be forgotten because of that. But if you use this kind of like distributed or like this kind of table memory, like in a hash table like that, you can actually be able to learn immediately, okay, and your memory will not be changed, okay, because your memory will be stored in a separate index. Okay, this is the unreliable storage part. Okay, one good thing about neural networks is that they interpolate well. Okay, whereas for memory, okay, in order to like retrieve a similar memory to use in a similar situation, you kind of need to store the memory in the right abstraction space. So this is one part that needs to be looked into, like how do we generate the right abstraction space for your memory? So one way to do this would be to use some form of like autoencoder to get the latent space and so on. Yeah, there are many ways to do this. So this can be looked into. But if you can get the right abstraction space, your memory can actually be used as a means to generalize. Like when I face with a similar scenario, I can just retrieve a similar memory and I can perform the same kind of actions. Right. So this is actually quite exciting. So there's a use for both systems, but the memory system can actually be key to learning a lot of new skills very fast and efficiently. Yeah, I mean, if you look at the patients with hippocampal damage, all right, they lose the ability to form like new memories. For example, HM, like Henry Molaison, right? They actually find that if you have hippocampal damage, you have difficulty like learning a new skill. I mean, you can learn something that you have done before through, or you can, or rather, you can learn like a new motor skill maybe through repetition. But in order to like learn like other stuff like knowledge, semantic knowledge, or this, it actually takes a lot of effort, or it might even be impossible. So there's a role for this memory in our learning systems. Okay, you can learn a lot more effectively with memory. Okay, and that's why we try to model memory into this learning agent. All right, so let me just quickly move on. Okay, I spent too much time on the memory part, but I'm very excited in the memory part. All right, so the next thing that a gripe that I have with current reinforcement learning systems is that we typically use the value-based methods to actually do our like next state prediction. We choose the action that leads to a higher value for the next state. Yeah. So this state can either be the value associated with the state itself or the value associated with a state action pair. Like at the current state, I take a certain action. What is my value? So this is called the Q value. So typically in like tabular cases, it's done using the temporal difference error. So this is the reward that I get with a one-step look ahead. So if this is my current state, I take an action. I go to S prime here. So it is like the value of this S prime. And then plus this reward over here, you actually sort of update the value of this state here with the value of the one-step look ahead, which is this part here on the right. So by doing so, we get a more and more accurate look ahead at the earlier steps. Okay, but this actually is also an issue. So let me just describe this again. So the issue of doing these value-based methods is that if your reward is kind of sparse, you kind of need to backpropagate your one-step like Bellman update one by one and so on, all the way until like the start state. So that will take a while to learn. Okay, like actor critic methods like PPO, they do like the discounted value of the discounted rewards, okay, for all these states and update them all at one shot. Okay, so they try to bypass this method, but there's still another problem with like value-based methods. Even if you do it in a more efficient update like what PPO does, there's still another problem. And the problem is that the value will be based on your goal, the position of your goal. So whenever, like, let's say the door changes over here, you kind of need to learn a different way to go to this door, right? So you need to learn a separate value function for that door. So there's this paper by David Silver. It's called Generalized Value Functions. So they do a value function not just for the state, but also for the goal. So for each goal, you define a certain value function and you learn that value function for that goal. Yeah, so this actually is also a very slow way of learning because you need to learn all these value functions for different goals. All right, so my insight is that, why not just do away with the value? So the key purpose of having this value here is to catch your experiences. So in the game of Go, if you already know that like going to this board state is bad, then I won't go there anymore. So you actually have a way to cache your experience. Like let's say if I know going to this square is bad, I'll give this square a very low value and then I won't even go there anymore in the future. So that's the benefit of having these kind of value functions. It is great if your environment doesn't change and you can just keep learning this value function through your experiences again and again, and the value function will be very accurate. But the moment you have this kind of changing goals like that, your value function learning can be very slow and not just slow, it might be even uninformative because what you learn in the past may not be relevant anymore in the future. Okay? So granted, okay, we do have this kind of temporal difference error in the brain. I do think we use value predictions for some parts. Okay, but for the agent that I'm describing, where we want to like go towards the goal, probably we don't really need this value-based method. I mean, who knows? Maybe this can be incorporated in this system as well. But this definitely is a slow way of learning. Okay, maybe it's all right if we incorporate some fast way of learning and then the slow way is another system. You let the two systems compete to see which is the better output. So I acknowledge that a value-based method might still work in the system that I'm proposing, but as another parallel branch, all right? So, the brain can consist of many decision-making systems and you just choose the best one for the job. Yeah, so there's a point for this. It's just very slow to adapt. All right, so this brings me to my next slide. Can we use goals directly without the value function? So I'm not sure whether you all have thought about this before, but like, why do we do what we are doing right now? All right, why do humans do what we're doing? Why are you listening to me right now? All right, do we do that because like you calculate the value function, or is it because like you want to achieve certain goals, like maybe you want to ask some questions, or like you're curious about the method? So in a more fundamental thing, like humans, when we explore, we kind of explore for food, for shelter, or if basic needs are met, maybe higher level needs like knowledge, that kind of stuff. Yeah. So one very, very key thing that I've discovered, okay, because I have a kid, all right, is that the idea of random exploration just doesn't seem to hold, okay, because there's some literature called intrinsic rewards where they reward curiosity. So if let's say if a new state, exploit, new unseen state, we exploit. So this idea of intrinsic reward with curiosity-driven exploration kind of fails when it comes to like how humans learn. Okay, let me give you an example. So I think Tsari has probably heard this before. So this is the idea of the combination lock. So let's say I give a baby like a combination lock, and then I start off with like numbers 001. Maybe the baby will play until like 002, 003, and so on. After you reach like 005, maybe the baby is bored already. Okay, because the baby probably has figured out how the lock turns. But if let's say the goal director is to unlock it, all right, humans are generally not very curious to look at every single combination to unlock. In fact, it's a chore to go through that combination lock and unlock it. But the AI agent with the curiosity-driven reward, they will just go through every single state until it opens. Right? There's a mismatch here. And what I think is going on is that this curiosity is not in the curiosity of your state space, but more of the curiosity in like how things work. So as long as the baby learns how the different rotors turn, is happy with like building a certain model of how the things work, and that's it. You won't explore like a new state. Yeah. So okay, the idea of this is basically the way we explore is highly like goal driven. All right. And the goal itself is also not like a very, very grand goal like soft AI. That kind of grand goal is a little hard to contextualize, but these goals are actually more like what I call sub goals, or like attainable goals. So a goal could be something like this. Like you start from a forest here. Okay, let me use the red color. You start from this part of the forest, and then you want to reach like a high tower in the middle of a forest. So you don't know how to go there, but you can see where the tower is. So you just head straight directly towards the tower. That's the most natural gut instinct. Okay, but let's say if you have like a river bank over here, you actually have only the bridge at a certain point here to cross. You don't know where the bridge is, but you just head towards the rough direction of the tower. Once you hit a roadblock, maybe you just go along the bank, and then eventually you find a way to cross the river, and then you continue moving towards the goal like that. So using this kind of goal-directed exploration, you can actually like sort of find an initial kind of direction to head towards. That direction can be approximate, okay, but it doesn't really matter, because what matters is you try to head closer to the goal if possible. And one way of implementing this is to use like perhaps a neural network, given a current start state and the goal state, generate the action. All right. And in order to prevent yourself from like visiting like states that you have already, you can use count-based methods to prioritize states that you have not seen before. All right. So actually it's something similar to this intrinsic reward, okay, applied to this count-based methods. All right. Another point that I want to say is that, like, earlier on in my previous work, okay, I tried to use a goal-directed intrinsic reward in order to basically use a form of heuristic, like for example, a Manhattan distance to the goal, to prioritize like certain actions that will lead to a closer like such heuristic to the goal. Okay, but as what some of the reviewers have told me, this actually is very handcrafty, like it's quite handcrafted and may not work for all kinds of environments. So as a takeaway, I kind of invented this hippocampal replay method in order to train this goal-directed system so that we don't even need a heuristic at all. We can just use our experience to train what the next action is. All right. So this is all quite cool and stuff. Let's okay. I just pause here first. Any questions on this slide? Okay, if not, let's go to the main architecture. So this is the main architecture. As what I said earlier, this part here is the goal-directed. Oops. This part here is the goal-directed part. Actually, both are goal-directed, but this part is using a neural network to, given the start state or current state and the goal, generate the action. So this gives an initial approximate direction to head towards, right? Then we can actually do some form of model planning, look ahead. So this is like model planning, look ahead, using memory. So this is the more accurate way to plan because it's more accurate. Because if you can form like a sequence of actions based on your memory towards the goal, you can just use that sequence of moves again and again. So that is like how you travel to your office building with the 2 doors. That kind of thing is more accurate, but it takes longer to process. So like this is my take on episodic memory. Actually, all these memories can be used in order to help you in a similar situation next time. So that's why we store this kind of memories. So what we do is we start with start state and a goal. And you know, in the neocortex, there's like mini columns. So I posit that each mini column could actually be a parallel agent. Each agent will start with like maybe start with the state 1. It queries the memory to see the closest match to the current with a random action, and then goes like maybe state 2. And then you go on, and then like you get state 3. So let's say if your state 3 is your goal. Okay, so state 1, state 2, state 3, this is actually like perhaps a trajectory of length 3. Okay, whereas when you can go here, state 1, maybe you query the memory, you get state 3 directly. Okay, a trajectory of length 2. So what should we do? Length 3 and length 2, in order to make it like more efficient, like you want to get to your goal faster, right? So we just use the trajectory which is the shortest. Okay, choose the shortest trajectory. And if we can find the shortest trajectory, the first action of that trajectory will then be used for your next state. So the next state, what you will do is you will then use action A or whatever action that you have found here, and you can then override the action of your fast neural network. Okay, so this fast and slow has some parallels to like Daniel Kahneman's thinking fast and slow, right? Because like fast is automatic, something like how the action is generated automatically by your neural network, while the slow is more deliberate. You need to take time to think through like where, like how can you go there, you know, that is somewhat accounted for by the memory mechanism. Okay, Evan just asked, is there such a thing as fast retrieval, fast learning? Yes, of course. I mean, because the memory mechanism, you store things fast. Like the moment you encounter an experience, you store into the memory. So that is fast learning. Fast retrieval is probably like how I described the memory retrieval just now. Like you just push out to all your like different memory locations, and then the closer you are with the match, the faster you return back. Then that is like a linear time. You know, you don't scale with the amount of memory because it is a parallel processing system. So yeah, you can definitely get fast learning and fast retrieval. Okay, so that's the memory system. All right. Oh yeah. So over here, I say slow retrieval. Okay, slow retrieval. Okay, why? All right. Although I say that, okay, memory, you can like take things fast. This slow retrieval is because of the look ahead, actually, mainly because of the look ahead. The look ahead takes time because you need to query the model and come back. So it's like a for loop. So this part here, unfortunately, the longer your sequence, the longer the time it takes to recall that piece of memory. So of course, there's ways to like bypass this. Maybe you can have sort of a cache, I mean, somewhat like a value function to cache future state. I mean, so there might be a way to improve this. But as of now, based on this naive architecture that I thought of, it is still very much like a for loop. Hence, it is a slow process. Okay, and also the way that I retrieve the memories, okay, it is still somewhat in a like a dictionary manner, like you query the key and you get the value. Yeah, so that is still not as fast as like a neural network processing. Yeah, so I term this slow mainly because of the look ahead, but also the memory mechanism takes a while in order to get the single result that you want. Okay, unlike a neural network. Yeah, neural network I say is slow learning because it just takes a long time to learn the weights. Okay, if you are familiar with neural networks, it can take a few epochs to learn the correct like input output relation. Yeah, whereas for memory, if you just change the particular like entry in your memory, you straight away learn already. All right, so that's why it's fast learning. Yeah, so in all these two mechanisms will help the agent to learn better. Okay, so this is what I described earlier. The neural network predicts the best initial action given a goal. It's like the compass in the forest. Okay, it gives you the first initial direction. This is also coupled, okay, with the count-based method. Right. So the slow part is basically using the memory mechanism to do a potential look ahead and to see whether or not you reach your goal state in your look ahead. If you do reach your goal state, then you just use the action. Oh, William asked what's the consolidation state, right? So the consolidation state is basically if you have multiple trajectories written. Let's say you have one trajectory, it's like state 1 to state 2 to state 3. And you have another trajectory from state 1 to state 3. What I want to do is I want to prioritize this one because it's a shorter trajectory. So the consolidation is when there's more than one like value that you return, you choose the shortest one. And one interesting thing about this consolidation is that it can be done in a lateral inhibition kind of manner. So let's say this is state 1 to state 3. And because of the way we do like the memory retrieval is somewhat like a for loop, you need to keep looping for each state, then do this, the next state you do this, next state you do this. You kind of sort of like have a chance that if this is like state 1 to state 3, and here is state 1, state 2, state 3, your state 1 to state 3 more often than not will return first. And if it returns first, what we can do is we can then do this thing called lateral inhibition. If this thing comes through your system first, all these are parallel processes. If this thing comes through your process first, you get the answer already. What you can do is you can then terminate all these processes and you can just run with like the first action here. So you can apply some form of lateral inhibition. We just take the first return value. So it seems to me like in my study of like neuroscience that the brain is massively parallel and we do a lot of parallel processing. Yeah, because if we were to do sequential processing like how the neural networks do right now, we will need like more than 1 second to make a decision or even more than that. So we are able to make decisions in a very fast time, although our action potential process takes a while, a few milliseconds, all right, unlike a computer chip. And the reason why we can do that is we actually process things in parallel in a lot of areas, like especially the neocortex with all its mini columns. So when I thought of this architecture, I was inspired by the neocortex and the mini columns. Yeah, I'm not sure if you all heard of this person called Jeff Hawkins. Yeah, he's the founder of Numenta, and he basically expounded a lot on mini columns, and I'm actually a fan of his work. So this actually in tribute to him. Yeah, I really think this memory system is correct. I really think this is correct. The only thing that should change is perhaps like how do we store the memory, and like how exact do we store the memory? Because if you store the memory in not the input stage, you store it in the abstract space, maybe you can generalize better. So all this can be done, some experiments can be done, but overall the idea of the mini columns or like the different branches processing, and then you take the more efficient thing, more efficient path, this actually helps to train your fast neural network. Okay, this more efficient path thing, okay, is somewhat like supervised learning. You pick the best possible state, action sequence, and then you train the fast neural network. All right, this is very important. Okay, because like in cases like AlphaZero, you kind of use a bootstrap method. You learn your value function and policy function from like your earlier value function and earlier policy function, which I've done experiments on AlphaZero before. It takes very long to train. It took like about 1 month in order to be superhuman at a tic-tac-toe game, 7x7 board, Connect 4. It took 1 month for it to be competent. And even so, I changed the environment a bit, it loses to me. So yeah, this is the problem of bootstrap learning. If your earlier network is wrong, your later network that is based on the earlier network will also be wrong. Okay, so this part where we use the shortest trajectory to learn, this is something like supervised learning. It is more efficient. Reinforcement learning is not very efficient, but supervised learning is pretty efficient. You have the sort of the right label, because this is like the more optimal label. So I mean, for those computer science folks, this kind of look like Monte Carlo sampling, because like I just do random sampling to get like random trajectories, and then I just take the trajectory that is the shortest and I learn from that shortest trajectory. So this actually done in the Meta is like Meta is the company. Yeah, Meta has this thing called the hypertree proof search. Yeah, they also use the shortest proof that they find, and then they learn from the shortest proof, like what's the next steps and so on. So there's some parallels with this idea and like the hypertree proof search, where you just take the shortest path and then you learn from the shortest path. In fact, actually works like there's also works like alpha tensor, also take the shortest solution. Okay, I'm not sure if you heard of alpha tensor. Is the one that uses AlphaGo like algorithms to like try to make matrix multiplication a little faster. Yeah, so they also take the shortest solution and train on it. So it's a similar kind of idea to this kind of works. Yeah. Any questions so far? Okay, let's move on to the interesting bits, all right? So this is the interesting bit, right? This is one of my favorite slides, all right? So this is basically how a mouse learns like through hippocampal replay, right? So this is from Zhu and Frank, a neuroscience article on how the hippocampal replay works in mice. So if you take a look over here, you have, this is your start state. This is like the start state, and this is like the goal state or the end state of the environment. You can see that this like activations in the hippocampus correspond to like the different color plates that the mouse has been through. So like they recognize the area by the color, and this is the corresponding activations in the hippocampus. So we actually like have the ability to go through two kinds of replays. One, I call it the previous state replay, and the other one is called the forward state replay. All right. And both of them have a forward and reverse direction. So for example, this is like your current state, start state, current state, and your end state here. So you can actually retrieve the memories forward. Then you go backwards from your retrieved memories. And the same trend happens here. Okay, so for years, people have been saying that this hippocampal replay could be some form of value consolidation, okay, because we use the value framework. The earlier states could consolidate the values from the later state, and then we backpropagate the values downwards. Here, I'm proposing, okay, this is, as far as I know, this is quite new, okay, because I thought of this recently only. So what I'm proposing here is that this hippocampal replay is not just only for value updating. Okay, maybe the value update can be used for another kind of network, or can even be used in conjunction with this fast and slow network also, if I figure out a way to do that. Okay, but what I posit is that this forward and backward is a way to train the fast go-directed neural network. Okay, why? Because memories can only activate like in sequence. Like you can only go from like current state to the future. You try yourself. You can't really remember stuff backwards. You try remembering the alphabet backwards. Like you can remember the alphabet forwards because we've been so used to it, like A, B, C, D, E, F, G. But it's very hard to remember the alphabet backwards. Okay, that's why this step here is necessary. The forward step is necessary because you want to read like maybe working to make sure that like get the highest sequence of states start to, okay, but backward, this is my what do you call it? All right, you need to first find the goal state, which is the last state. So here is the state, and then after we find the goal state, then we can use this as the goal over here. Then we can then train all the start states here one by one. Start state, start state, start state, start state. And each of these start state will be accompanied by a certain action, like action prime, action. Okay, so the action that you have taken at that point of time. And then you can then train this action here and the state here. Okay, you can learn for every single trajectory until your current trajectory. Every single experience state is your start state. All right, and then you can repeat the same thing for the forward replay also. If you find the trajectory with your memory retrieval, your final goal state is your goal state, and every single state in that path will be your start state. Okay, why do we do that? Okay, this means that every single experience state that you have is both a start state and a goal state, and it's very efficient. So let me give you an example. Okay, so I think this one Zuri has probably heard before. So let's say if I want to go from point A, okay, and I pass through point B, okay, and then I go to point C. Okay, if I figure out a path to go from point A to point B, point A to point C, passing through point C, all right, it also means that I've learned a path from point A to point B, right? And it also means that I've learned a path from point B to point C. And this is actually very efficient because you go through your one experience, you can repeat snippets of your experience for certain other goals next time in the future. So your one experience that you have is actually multiple experience for a diverse amount of goals in the future. So I quite like this idea. So you keep doing this hippocampal replay at every single time step of your episode until you terminate. Even if you don't reach the goal state, whatever that you experienced before is already your goal state. So there's this work in reinforcement learning called hindsight experience replay. Okay, it is like a subset of this thing. It's less efficient than this method because hindsight experience replay, what they do is they just vary the goal state. So like all these experience states will all be like randomly selected to be the goal state. Okay, but they don't have every single state as the start state. Yeah, so this is less efficient than the less efficient. Yeah, so there's some parallels to what has been done in reinforcement learning so far, and I think this method is very useful, very effective. Okay, so you learn from one stream of experience, you can learn many different things, and that's the idea of learning from limited samples. Okay, questions on this slide? Okay, yeah, let's move on to the results. I think the next is, okay, so this part is how the slow method works. So I already described it, but let me just like run through again. So you have B branches to parallel process. Each branch is like a mini column. Okay, and then what you do is you take the starting state here, you reference a memory, you randomly sample, and then you get the next state here, like state 1, and you get state 2. Okay, and then if like more than one match, you just randomly pick. Okay, you continue with the next state as the reference. So now state 2 is your reference. You go through memory, and then maybe come out state 3. And then once you have reached your goal state, you break, okay? And then this state 1, state 2, state 3 with this action A over here will then be passed on here, and then you get the action A at the end. Okay, use the shortest trajectory. Okay, so there's a chance that you may not get a sequence of states here because you may not reach the goal state. Okay, in that case, the slow memory retrieval network will not be used at all for decision making. You will just be using the fast neural network. Okay, so this is a potential issue when we scale out our state space because we may not be able to find the right trajectory of states to our goal. All right, so there will be more efficient methods that we probably have to use rather than random selection. Okay, we maybe have to use a way to do some form of distance metric. Okay, you have a distance metric between your next state and your goal, somewhat like a value function. Okay, like the generalized value function. Maybe it's useful after all. You can then prioritize picking things with a shorter distance. So that could be one of the things that can be done. It will take longer to train, but it might be more useful when you have a longer trajectory of states. Okay, let's move on. So this is the overall like secret sauce of this algorithm. So you start off with a current state and a goal state at every single time step. Oops. You start off with a goal state and a current state. Okay, what we do is we then use the fast neural network to get the action probabilities for the goal. All right, and then what we do is this is the action probabilities. Okay, so to illustrate this point, maybe we have like up, down, left, right. And then we have like probability of each action. Maybe up is quite good. So I get action of 0.9, down is 0.1, left is 0, right is 0. So what will I do? I will then select this probability here, because I will want to select this probability in order to prioritize like the initial direction. It's like my initial compass tells me I should hit up. So I'll go up first. Okay, then what is this term here? This is like the exploration term, all right? So this is your num visits. I put num visits here. If I visited up once already, okay, I don't want to go up again because I've visited that state before, all right? I want to prioritize other states that I haven't visited before. So assuming if I go back to the same state again, all right, the next action that I will prioritize is probably down, all right? Because if I visited this once, I penalize it a bit. So those states that have not been penalized before or have not been visited before will be given a higher value. And then next, I'll explore down. It's something like if let's say your maze is like that. Okay, at this current state here, if you have visited up before, and then you go like one round and then you come back here again, you know, you kind of don't want to go back the same path again, right? Because this path didn't work out. So you want to go down now. Yeah, so this is an example of like preventing cycles using this count-based methods. All right. So again, if we use the slow memory retrieval and we find a sequence of states to the goal, we use that action because that's the more accurate one. So we override the action. So that's the rough procedure. It's very efficient. All these memories over here, this num visits is taken from the episodic memory, which means that we set it at each episode. Because each episode, you don't want to like retain the previous counts, okay, from the earlier episodes because it's a new kind of problem maybe. Yeah. So this comes from the episodic memory. All right. The PA comes from the goal-directed neural network that is like trained across episodes. All right. So this is more or less how we do this. Okay, but this slow memory retrieval here, this slow memory retrieval actually uses the overall memory that's kept throughout episodes. Okay, because whatever you experience in the past few episodes might still be useful for the later episodes. So the memory retrieval, we use the overall memory. Okay, so the next part here, what we do is we update the memory retrieval network with the new transition. This is the O1 timing, where we just like, we learn immediately from our experience. Okay, this is important in this part here. In order to cater for changing environments, we need the memory to be updated to be the most recent for the environment. So if the memory conflicts with the current transition, like for example, if you move forward and you don't move forward now, okay, because of like maybe an obstacle or what, you want to remove away all your past memories that you could move forward at this certain state. So this helps the agent learn. So in some sense, updating your memory is updating learning. It's actually learning. It's quite radical, right? Your memories could be how you learn, because what you remember in your head is exactly like what you can use to reference for a future scenario. So memory is actually a very huge learning tool. Okay, it's even more huge than what you may realize. Okay, if I take away all your memories right now, you may not be able to do a lot of things. All right, so this is quite cool, right? Then what we do is then we perform hippocampal replay, okay, in order to update the fast network. Okay, so if you keep doing this, you eventually solve the episode. So you do realize that there's no reward here. The reward is only used like in order to end the episode, but we don't even need to use a reward function at all or value function in this entire procedure. Okay, let's move on. Okay, any questions, just feel free to ask. Oh, what's hippocampal replay? We need to ask, is this one. Hippocampal replay is using every single state as the start state, and then you do like the goal state here, which is the current state. And you start from the current state and you use the last state as the goal state, and then you train this network here using the start and goal pairs. So like, for example, this start state and this goal state, like you take action A here. So it'll be like S1 and like maybe GS5. Yeah, so like your start state can be S1 and your goal state can be S5. and then your action will be A1. Yeah, so this is hippocampal replay. Then you can do that for the next state pair, which is like state 2 and A2. Yeah, is that clear? Like state 2 and A2. Yeah, so this is hippocampal replay, which is learning every single start state and goal state based on the experiences that you have. Okay, let's move on. So I actually been singing a lot of praises of this method, but how exactly is it good or not? So let's try out with some experiments. So we do a very, very simple experiments to just give a proof of concept that it works. So the start state is 0, 0, end state is n-1, n-1 in the n by n grid. Actions up, down, left, right. The reward is 1 if agent reaches the door within n by n steps, otherwise 0. Okay, so do note the method that I'm using doesn't need the reward, but the reward is there because we want to compare with other reinforcement learning benchmarks like PPO, TRPO that uses a reward-based learning, right? So to make the problem harder, we make the agent not be able to see the wall. So you kind of need to sort of like memorize how to go from start state to end state because it may not be able to see like where like certain obstacles are. So you will only know the obstacles after you encounter those obstacles. So this is one of the challenges because in real life it's the same thing also. Like you may not be able to see everything. So that's why this part was modeled in to facilitate some form of partial observability. Yeah. Okay, let's move on. So this is the results, all right? So this one is new. Okay, I didn't present this on the last time. So fast and slow is the architecture that I described earlier. Okay, the number of steps is basically the number of like moves it took in order to reach the goal. Okay, so I said I didn't want an optimal agent, right? I didn't really need an optimal agent. The optimal number of moves is 18. Okay, because in a 10 by 10 task, you need to move upwards nine steps, and then you move on the right 9 steps. So the optimal number of moves is 18. Okay, although not explicitly planned for, but because of the way we do the memory retrieval by the memory mechanism, we prioritize the shortest states. So it kind of learned to do the optimal after just 2 episodes. So you can see that over here, like this is the zoom in version of the first 10 episodes. You can see that by the second episode, right, it has already reached the optimal in a static case. So how do the rest fare? All right, so the worst performing is this Q learning. The Q learning, because you sort of do random exploration. Okay, this is just because of the behavioral policy, you need to train it random and then you do greedy here. I tried to do a mix of random and greedy. I found that this is the best, okay, because you want to kind of search the area first using the random before you do the greedy. Okay, so this actually works. Like after 75 or 76 episodes, then you learn like the optimal solution. And I like to highlight that this is actually this tabular Q learning. It's actually faster than deep Q learning, Q network. All right, especially for this environment, okay, which actually kind of highlights that DQN is very inefficient. It takes very long to learn. Right? How do the rest fare? Okay, PPO is one of our best methods. Okay, it's also used in the ChatGPT. Yeah, so PPO actually fares. Okay, let's just take a look at this graph here. PPO actually fares not bad. It learns in about 6 or 7 episodes. Okay, not the minimum yet, but it's quite close. Right? TRPO maybe about 7 episodes. Actor advantage, actor critic, maybe about 8. Yeah, you can see that it's still learning over here, maybe about 20. Yeah, so you can see that the actor critic methods take quite some time to actually learn the episode. It takes like in excess of about around 10 episodes, compared to the fast and slow method, which within 1 or 2 episodes, it learned everything already. So this highlights the benefit of using memory for learning, as well as the benefit of using a goal-directed mechanism for learning. Okay, so this is the results for that. Any questions on these results for the static case? Okay, because of the good performance for this, I've decided to increase the difficulty of the experiments. And now we do it for the dynamic case. Alright, so the dynamic case is like reinforcement learning environments on steroids. All right, every single thing is difficult. Like the start and end state will now be changed each episode. So The start and end goal for the maze will always vary. There will be some obstacles which block certain squares that you cannot move. And these obstacle locations change without even telling the agent every 50 episodes. So this one, what I put agent is unaware of where obstacles are. Okay, so this is a very, very difficult problem. And it takes a lot of, like most RL algorithms or methods will take a long time to learn this environment because of the way it changes dynamically. So let's see how our algorithm fares. All right. So this is how the maze changes. All right. So initially there's like one small gap here. All right. And then you kind of need to navigate through the gap like that. And then after 50 episodes, the gap changes direction, like from vertical become horizontal. So the way you navigate has to change. So this is an ultimate test, right, to how adaptable the agent is. So this is the main results. All right. We can see that for 10 by 10, the solve rate for fast and slow is about 92%. Okay, compared to the next best method, which is like 54. Right, this for the 10 by 10. Okay, I've also done results for 20 by 20 and 40 by 40. I think it's about like 80+% for 20 by 20, and then TRPO is about 20%. Yeah, so there's some, basically the larger the grid, the more beneficial using this method would be. Yeah, but there's a caveat, of course. Maybe the way I implemented it wasn't that like optimized. It does take quite a long time to do the parallel threads for larger episodes. Yeah, so larger grids. So that is a problem that needs to be solved. But I think it's definitely solvable with the right computer language. Okay, Python is probably not the right language to use for parallel threading. Yeah, so I use Python. So that's why it turned out to be quite slow. All right. So based on this, okay, solve rate over here is like whether the agent reaches the goal within n by n steps. Yeah. So you can see that the solve rate for fast and slow is like super high, 92%. Okay, compared to the rest. So this shows the benefits of like the goal-directed memory-based approach. Then we also do like steps above minimum, which means like the number of steps it takes beyond the optimal number of steps. Okay, the optimal number of steps was calculated using breadth-first search. All right, and you can see that again, the fast and slow is way more optimal than the rest. Like it beats it by at least 4 times. Okay, this may not exactly mean that it's like the most optimal, but based on the fact that it solves more, all right, it's already more optimal. Okay, let me just do a caveat. Okay, caveat. If agent did not solve that episode, it is counted as n by n steps. Okay, so actually the more you fail to solve, the more you get penalized here. Okay, I mean, I could also do a case whereby I do the steps above minimum for solved episodes. You will still see a clear winner of the fast and slow method compared to the rest. Okay. Yeah. You have any queries for the results here? Okay. So given that the fast and slow is actually quite good, so we want to see like what exactly is needed in the fast and slow architecture. So we do some ablation studies on it. So the baseline is the original fast and slow method. And now we do the next part, which is like take away the slow memory retrieval. So there's no slow memory retrieval to override anymore. And you can see that it affects the solve rate, but not as much. Okay, it solves about 70%. If we take away the fast neural network, okay, and just output probabilities of 0 for all your actions, the solve rate is like 50%. It is impacted quite a lot. Okay, this also shows that the initial direction that you head towards is very important. Okay, and the compass direction by the fast, although approximate, is actually very helpful to solving the environment. Because if we take away the fast, okay, it actually impacts it way more, like 40%. Like this is actually 41% compared to like 21% for the slow. And the most exciting thing is if you take away both the fast and slow, and that means you only use the count-based methods. Count-based, it kind of takes like only solves it 22% of the time, which means that the count-based method is definitely not enough to explore the environment and solve it. Okay, you need the goal-directedness for both the fast and the slow to solve it. So this actually is a validation that both the fast and the slow learning mechanisms are important. Okay, next we then look at how we vary the different look-ahead depths. So the baseline is a look-ahead depth of 20 and 100 parallel threads. So it's 20 and 100. So we take a look at how this affects. So the increasing the look-ahead depth actually increases the solve rate, which actually makes sense because if you can look ahead more, you solve more. I mean, you have better trajectories. Okay, same thing for parallel threads. If we have multiple like retrieval processes, the more we have, all right, the better our solve rate would be also. So you can see that this is exactly what we observe. So one good thing is this thing here, parallel equals to increasing this comes at almost no time complexity. So we can increase the number of parallel threads and we can solve even more difficult environments at almost no cost at all. The only cost is that you need to run more parallel threads, but the time-wise is the same. So that's the beauty of parallel mechanisms. The only thing is like this look-ahead depth, you kind of need to, like, this actually incurs time costs. So for larger grid size or larger environments with a very long horizon of actions, your look-ahead can be quite costly. So this one can be future work to try to reduce the time cost for that using some catch values. Yeah. So next slide is on the steps above minimum. You can see that the parallel threads here, okay, again, increasing the parallel threads like is actually quite good. And same thing for the look-ahead depth as well. But here, increasing the parallel threads actually help to find the shorter trajectories more easily. So this parallel threads is in direct conjunction with optimal and efficient solutions. So the more I have parallel threads, the more optimal I become. Yeah. So yeah, although the agent wasn't planned on achieving optimality, through the very fact that we take the shortest trajectory and learn from it to learn the goal-directed mechanism, it actually does very well. So that's quite interesting. Yeah. Also, I would like to highlight for the memory mechanism, we don't exactly store the goal for the memory. You realize the memory mechanism is just the following state, next state, and action. Yeah, so it is purposely done this way. We don't store the goal for each state, because if we were to store the goal, you know, the chance of you having a similar state and goal, like in the next case, might be very rare, all right? But if we just store the transition, you can then use this state, next state action in order to like use it for any arbitrary goal. So that's one of the things that I think is done correctly. All right. Okay, so this is the rough conclusion. Okay, before we like do some questions. All right. All right. So the key thing is that the memory mechanism is very robust. It can enable the agent to learn. Oops, sorry. Can enable the agent to learn very fast. My mouse. Okay, enable the agent to. It can. Okay, they can enable the agent to learn fast when the environment changes, because we can just update the memory mechanism. This is way faster than updating the neural network. And so the neural network itself, it can take a while more to be updated, but at least for the last mile, like goal finding, the memory mechanism is updated instantly. Okay, we can increase look-ahead depth and parallel branches to improve the memory mechanism performance. Okay, using count-based only without the fast and slow is not sufficient. So this is like a proof of concept that this memory and goal-directed kind of network is useful. And lastly, using value-based systems like actor critic. Okay, actor critic also has the policy network, which is like quite similar to the goal-directed fast network. Okay, but because they also use this value thing to like learn from it, it actually converges quite slowly and it adapts quite slowly. So these are the key findings from the research. And let me just spend about 5 minutes talking about like what I intend to do for future work, okay, before we break out for some questions. So these are some extensions that I've been thinking of in order to improve this work. So the first one is multi-agent learning. Okay, actually you can just read through here. I have 4 slides to go through this. So let's start with multi-agent learning. So, you know, humans, we are not exactly an intelligent species if there's only one human. Like more often than not, it's because of a group of humans working on maybe the same problem one of them finds a breakthrough and suddenly everyone can find the breakthrough. Okay, the most evident example of this is ChatGPT or large language models. Like large language models work, and suddenly everyone is working towards large language models, transformers, and using it for different domains. Yeah, but you just need like one person to find the thing, and then you can use it. Okay, this can be good and bad because like this leads to like maybe overly narrow specialization. But at least it shows that as a species, we actually can learn from each other's experience. So what if our shared memory bank can be the same? And at every episode, we have n agents like running through the grid, and each of them have different hyperparameters, different random seeds, and so on. And if one of them finds the goal, that sequence of actions to the goal will then be passed on to this shared memory. And this shared memory can be updated instantly because the memory is just a key value pair, right? You can update the dictionary instantly. You can return it back to all the agents. So this idea of sharing experience is of course not new, but the shared memory bank thing might be new, all right? Using the shared memory bank to pass on this memory to everyone. So this is something that can be done, all right? I think this will be quite interesting to see what's the potential gains using multi-agent systems to learn from that shared memory. Okay. Next up, we have these arbitrary goals and sub-goals. So right now, the goal and sub-goal is like kind of predefined. We already like give it the end state by the XY coordinate. But what if we want to do like a very long chain of events? Like for example, if I want to go to my office, I need to sit on the car first. So I need to go to the public transport and then sit on the public transport, go to the destination, and then like walk to the office. So all this like different sub-goal planning, it's not very obvious how we do it. And recently there's this work called say can, or do as I can, not as I say, which I thought was quite cool. They actually use a large language model. They prompt the large language model with the goal. So this is the goal. Like how do I put the apple on the table? And then what they do is they query the model with this format, like number one, I will do something. So the large language model will, through its experience of what it has so far, it will like offer some suggestions. Okay. But these suggestions might be nonsense, okay? Because large language models don't exactly have a fact checker and so on. Yeah. But what's cool about this paper is that the agent has a value function that can like evaluate how good this action is to solve a goal. So actually this value function is a goal-directed value function. So if let's say I put apple on the table, like the more relevant ones will be to like go to the table first. Yeah, so this basically is like the next step. So like the first step is like you need to query the model, like what you do for the first step. Sorry. So the first step will be like here. The model queries the first step, and then based on the combined score of the large language model plus the skill affordance, you get the first action, like find an apple. Then from find an apple, you then query the model again, and then what you get is this second part here, which like go to the table. So we go to the table. So you can actually create a sequence of moves until you reach the last move, like maybe 3 is done. Yeah. So it's like a way to generate sub goals. And the beauty is you can do this to do a chain of goals, or sorry, series of sub goals to achieve a goal. Okay. And also another beauty of like this kind of system is you can define your goals in natural language. Right. And then probably what you can do is you can then use the latent vector as the goal state. Yeah. So this is something that I think is quite interesting. And yeah, we can definitely use this to perform arbitrary goals. All right. And I haven't tested this out, but this is a promising direction, especially with the increasing use of large language models. I think it's very expressive, and perhaps it can be combined in this system to model arbitrary goals. This is one thing that I was thinking about also. I think memory forgetting is quite important for learning. In this system, I did not implement memory forgetting, but if we can implement some form of forgetting, okay, where if you don't retrieve the memory, you gradually forget it. Okay, and if you retrieve the memory more, all right, you actually like increase the strength of the memory. Yeah, this can actually help the agent find out which experiences are actually more relevant and which are not. Okay, so if those you don't retrieve often, probably not very important for you right now, then you can just forget them and make room for other memories to be stored. Okay, and this helps to make sure that the memories we have are useful for the current environment. And this actually is one way to view this. Okay, it can be this thing called the Ebbinghaus curve. Ebbinghaus forgetting curve. So Ebbinghaus is a researcher. He made a list of like, I think 100 over words of nonsense words, and he tried to remember those nonsense words. So he found that like after a while, he like forgot a lot of them. But if you revise them again, the forgetting time is actually longer. So the more you access your memories, the longer you take to forget them. So if we can implement a mechanism like that to forget, your memories will be more relevant for the current state itself. And I think this will actually help improve performance. Okay, of course, other things to look at is like how strong to store your initial memory. Like, there are memories like flashbulb memories or highly emotional memories that you remember for life. I believe emotion is very important to determine like whether or not a memory is worth storing. Like for very boring activities, like maybe studying in the university, you probably will forget most of it. But for very exciting activities like near-death experiences or very, very happy moments or very sad moments, you can remember for life. So this kind of high impact actions probably will be encoded for by memory, by emotions. Your emotions are probably a reflection of how important that memory is. And then you can like store that memory based on like some form of emotion. Okay, so these are just some ideas I have, and this can be future work. And of course, lastly, you all know of Yann LeCun. Yann LeCun has this path towards autonomous machine intelligence, where he has this architecture called the JEPA, Joint Embedding Prediction Architecture, where you like predict stuff in the latent space. Okay, so I don't agree with the latent space prediction part right now because it takes very long to predict. But one thing that he talked about in the paper is this hierarchical planning, where you have a sequence of actions over here. All right, these are low-level actions. All right, like for example, walking, like move your left foot, right foot, left foot, right foot. And then these are higher level actions. So these are low-level actions, low-level planning. And these are high-level planning stuff. So what we can do is then we can just use this high-level planning here. Like if let's say this is walking, this is like move left foot, move right foot. And then the higher level planning, maybe the action is like move left, move towards, move forwards. Yeah. Yeah. So your move forward is equivalent to like maybe a loop, move a left foot and move a right foot. Yeah. So this kind of hierarchical planning can help to do like higher order thinking, which is like, for example, if I want to go to my office, first I need to go to the public transport place or go to my car. Then I need to drive the car. Then I need to park the car and then go to the office. So that's the high level one. And then the lower level one is like maybe how do you drive the car? What's the mechanisms used? Yeah, because you don't exactly want to go to the lowest level all the time. It can be very hard to plan like that. Memory retrieval mechanism. If your goal state, if your sequence of states is very, very long, you need to look ahead a lot more. And that's very slow because the look ahead method kind of takes time. But what if you can do planning in a more abstract space, a more higher level space? And then based on what you plan at a higher level space, you can then use that as a goal. So whatever you plan here, move forward can be your goal. Okay, this can be the goal for the bottom system here. All right, so you can do some form of hierarchical planning with the goals as your higher level planning outputs. So the action over here that you decide for your high level will be the goal for the lower level. And I think this is very, very useful for a lot of planning problems because you can then reuse certain actions like move forward. This can be a goal for like, you can do this for like playing soccer. You can use this for tasks such as navigation. Yeah, so you can reuse the same like lower level actions in this goal directed manner to a higher level task. And talking about compositionality, or reusability. This goal-directed system with multiple layers of goals, you can actually reuse those sub-goals for a higher level planning, which I thought it was quite cool. And yeah, there's also another benefit of doing this, is that you don't have to like plan so detailed. You can just plan at the next possible level. So the amount of planning steps that you need to look ahead will be much shorter also if you use this kind of hierarchical planning. Yeah, so that's an idea that I have. Okay, so we are down to the last part, okay, which is the questions to ponder. All right, so yeah, maybe I just go through the questions one by one. If you have anything, you can just chip in. So like first is, how can we find the sequence of like trajectories or sequence of states maybe to reach the goal? Okay, because with increasing amount of like state space, if you just use random sampling, you may not random sample well enough to reach the goal. So I mean, I talked to some of my friends about this. I think apart from random search, maybe we can use some form of distance function where we can like evaluate this distance function with like the current state and the goal. And then we can just train this distance function, okay, with like the current number of like distance to goal based on number of states. So you can actually like learn the number of states using some form of a value function when you do the memory retrieval. So this process, or rather you can learn this transition, you can learn it from experience. Like whatever you experience, you can then do this distance function. Yeah, so, or you can learn it also from the optimal memory solution. Yeah, it might be better to learn it from the optimal memory trajectory, because then your distance function will more or less be the true label as much as possible. Because if you learn it from experience, this might be a little noisy. This one can be noisy. Yeah. Yeah, you have any other things to add for this? Like, if we increase the state space a lot more, how can the memory mechanism like output the right answer or right sequence of states? Yeah, is there a more efficient way to search through to do the look-ahead planning? Okay.
Association.
Okay. Maybe you want to elaborate more on that?
You're talking about efficient retrieval of memory, right?
Yeah, towards the goal. So a goal-directed retrieval of memory.
So, I mean, it's just an intuition, nothing very technical. Just instead of brute force search, like how we as human does it. Like when we want to solve some problem, you trying to link back to recall something you think might be relevant, right?
Yep.
So I think you are trying to associate in your memory or knowledge base anything that's related, in some sense related to whatever task you want to solve. Yeah. So that could be, I think that's a interesting things to.
So you store the goal in your memory base, is it? In your knowledge?
No. It's like in a deployment, right? Then you have some task to solve. So you want to know which part of memory is more relevant or more helpful for this task. So you want to have a retrieval mechanism that can tell you which part of memory is most likely to help you to achieve this task instead of just brute force search.
So it's some form of informed search where you prioritize your search based on, is it something like this goal distance function? Like the
but I think it could be tricky to define. This is like, that's why I talk about association. Like, how do you associate? Like, what kind of metric?
Okay. How similar the state is to the goal state?
Yeah.
Some form of similarity metric.
Like what I mentioned before, in high dimension space, it's not. I think it's not a trivial thing to do it. Yeah.
Yeah, maybe you can use that as a metric. Yeah, this can be possible.
No. My point is like to measure the similarity in high dimensional space is not trivial.
Oh yeah, of course.
Yeah.
So what?
So maybe just L2 or Euclidean just completely break down. You have to do something else. Yeah.
Yeah, so what I'm thinking is maybe your way you store your memory, your key value table, perhaps the way we store the memory is already in the high dimensional space already. So yeah, that's one of the things that we can talk about. That's the last question actually. This is a very important question. Yeah. But anyway, thanks Larry for the inputs. Anyone else want to say anything before we move on to the next question?
Building on what he says, I'm wondering if it will be feasible to like store the the memory in a form of like a graph. So like the
Okay.
edges would be like, I don't know, will have weights, so like and could be directed to tell you that which is like what things are associated with others, that kind of thing.
So it's a directed memory graph, right? Like state 1,
Yeah.
2, state 3. Yeah, definitely. I think a graph structure is very natural to represent memories because like after you activate a certain memory, usually you activate the whole chain of memories. So definitely some graph structure would be interesting to model. I mean, in some sense, the table that I'm trying to model is sort of a graph structure. It's just not direct. Like you have a key and then you can then like take certain action and go to a certain state. Yeah, it is sort of a graph. It's just modeled in like, it's just stored like that. Yeah, but you're saying that we can store the entire graph, is it?
Yeah.
I
Yeah,
think
I
that
didn't realize you were talking about graph previously, but okay. Thanks.
no, I think your idea is interesting because I've been thinking about it also. Can we store the memory as a sequence of states rather
Yes.
than I mean this RL, but of course you are doing generic memories, it could be a graph. Yeah.
Nice.
Yeah,
Okay.
is last time I also mentioned the knowledge graph thing. But I think one of challenging thing is how do you grow your knowledge graph? If you want, because you want to learn it, you don't want to hard code it, handcraft it.
Yeah. Though knowledge graph, you mean like semantic graph, right? Like those relational kind of knowledge, right?
Not sure what's that, but it's like basically it comes from common sense. What I'm talking about.
I
Yeah, it has to. So basically, you have to provide the agent with this knowledge graph. Then it can do some association based on that. But if it's, is it possible to learn this graph in the first place?
like you can do some sort of like relation graph, right? Like semantic web, and like you can like do like gender is male, and are you talking about like this kind of knowledge
Yeah,
graph?
but you provided the agent with the information, right?
Yeah.
But in the case of ourselves, we build this knowledge graph by ourselves. We don't. I mean, not entirely, but we do to a very large extent build it by ourselves.
Yeah, definitely. The knowledge graph building, I think, is very important. Yeah, and actually, increasingly, I think knowledge graph building can be done like implicitly by a transformer. Yeah, it's just that the graph will be very fuzzy.
I agree. I agree.
Yeah, I mean, I was thinking initially that we should have a external knowledge graph, but I do think that retrieving the knowledge graph will be very, very time consuming and
No,
like how
because
exactly.
if you already have an existing knowledge graph, then it simply means you shape the difficulties from the RL part to like you already solve it for it.
Yeah.
So you already make the task much easier. You provide it with this structure for you to search in a high dimensional space. Yeah.
Actually, it sounds very
But
similar to this method, right? Like you use this can be sort of like a knowledge graph, right? Like a knowledge of like what actions to do.
that's true.
And then you ask the query the large language model, and large language model come out with nonsense sometimes. So I feel like this secant thing is very impactful. I think they got some parts of it right already. Like you can use
And to tell you the truth, I've been keep testing on ChatGPT. It's become more and more impressive on this kind of task.
Yeah, actually, ChatGPT could be, or a GPT like architecture could be the way to do arbitrary kind of
And,
expected stuff.
and I think the most important thing is For example, if you try some, like previously we have seen like make some stupid mistakes, right? But now if you try again and you learn from it, it won't make the same mistakes. If it is
that's
not
provided that is within like 1,000 words context, right? Because if you go too far behind, it will not remember.
but we are talking about the retrieval of the association of memory, right? It won't be that long, I think.
If
But
you are saying that the like ChatGPT can learn as you type, basically the neural network weights can be updated instantly as you type your
no, because they also do in-context learning, which means that they can learn without changing the parameters.
Yeah, if with the right prompts, you can change the output of the model already.
And this problem already become like it don't need a very contrived to make it work. It's already very practical, I feel. And I think the most important thing is assume. I just say assume that they just train it like without much. It's just a semi-supervised manner. Means that you don't provide this structure I'm talking about to it, then it can learn it on its own. So if that's true, then yeah, I think that's one way to go to learn this knowledge graph. Then based on that, you can have an easier time to do retrieval, memory retrieval to you find the most important memory to whatever task you want.
Yeah, I mean, I do think memory retrieval, if you want to do like some form of directed retrieval, maybe you can ask the language model like what is the best area to search. You know, it's something like what you see here. But the memory model might give you, if you use a transformer as a memory, your memory model might give you like wrong stuff like that. So you still need some form of grounding. You need to ground it somewhere. So like either you ground it in a real knowledge bank, or like over here you ground it with value functions. I think the idea of grounding it correctly is actually a difficult problem. Because like how are you going to ground something that can generate arbitrary text, right? Like
I can think of two ways. One is you to minimize the error. First, you give it the specific context that makes it much easier to do. Second, maybe your RL can also be the role of a critic, because like your value function, if you can, I mean, if you can use the value to tell whether it's correct or not, then it's a critic to the retrieved memory. Right? It means if it's wrong, means your memory is not that useful.
That's interesting actually. Yeah, I didn't think of that. Like you are saying that you use the like transformer model as a critic, is it?
No. I use your RL agent as the critic to the transformer, the kind of so-called relevant info it provided. If it doesn't help your task, it simply means it's not helpful, right?
Oh, actually, then what you're saying is exactly what this thing is doing. This is actually the RL part. Then it just like sort of like tells it, okay, this output, is it good or is it bad? So I think there's a lot of relevance to this. Like large language models can tend to output nonsense, but if you can ground it in some way that is relevant for your task, it can be a useful way to.
So I think one very important thing to make it work is you have to be able to tell like whether it's useful or not.
Yes, correct.
When it's useful, it becomes very useful.
Yeah. So actually we can use this kind of large language models or sampling. Maybe you can sample the next state. Actually, I'm not even sure whether like a transformer model would be a good way to model the memory rather than the hash table. You see over here, okay, let me just show you the fast and slow method right now, right? The memory is this memory here. Oops, like this. I'm thinking, right, like will like ChatGPT style be able to learn this kind of table? Yeah, but if it can learn this kind of table, then it will be like quite similar to this kind of memory on the left here, right? The benefit is that you can store like arbitrary huge amount of data. The benefit is like you can probably retrieve it in one pass.
Wait, sorry, your table is more akin to the right hand side, right?
This one, key value pair.
It's more akin to the thumb drive, not the neural network, right? Because you know it discretize, and you change one entry won't affect another entry, right?
Yeah, no, I'm just thinking whether or not, you know, a transformer method would be also just as good.
I think so, because it can even simulate rule-based system.
Yeah, no, because the benefit of using a transformer method rather than this method is that you can model arbitrary number of states. Like there's no issue of your memory space exploding.
Yeah, but I thought you were also asking whether it can like model this kind of table, right?
It definitely can model. It's just whether accurate. I'm just thinking whether like an inaccurate modeling can still be useful. Yeah, then the retrieval will be very easy also. If you use a transformer kind of model to retrieve memories, you can give it the right prompt and you can get a memory already.
I think if you still remember the paper I shared with you, to some extent, it does localize the storage of information. The mass editing one. So I think that's the evidence suggesting it does somewhat localize the store of information. So yeah, so say it won't be as bad as a vanilla MLP.
Yeah, no, so actually there's also a problem of inductive bias here. So if you use like a hash table, you are very sure your memory retrieve is correct. But if you use like a transformer or a large language model, you may not be that sure that is correct. But if you can actually like, okay, so how I view this is that although the transformer may perform the same function, the way that we store the memory in the hash table will actually give us the grounding already. In some sense, it grounds us in the truth. Yeah, so there may be actually, it might still be beneficial to keep the hash table separate, but in order to retrieve my next state based on like over here to like sort of sequence of trajectories, right? Maybe a transformer might be helpful. You ground it in the truth table. We ground it in the key value table, which is like the memory bank. And then using that memory bank as the grounding, you ask the transformer to come out with the trajectories. That might be useful.
But then if you want to make use of your table, that means you need to iterate through the table, right? How do you solve the speed issue?
So you can have a way to basically, when you sample from the large language model, you choose the samples that correlates to an entry on the table. Like you give higher weightage to, of course, yes, if you have a lot of entries on your table, your like criteria, your evaluation criteria time might be quite long because you need to like sort of make sure that the thing matches.
I think if you make your table in some structure, it's possible to reduce this.
Yeah. In fact, you can even use this for fact checking, I guess. Yeah. if you want to talk about using ChatGPT stuff like models for search, you probably need some form of memory table for your facts also, or semantic web for your facts. Yeah. So I think people will be researching this area quite actively. So
but I thought like merging those kind of language model with internet is already in the sense internet is your table, right? It's
but your internet may not be a factual table, you see.
I understand that, but that becomes another issue, right? Of course you want to assume your table, whatever inside your table is already true. That's the assumption we have.
Yeah, but definitely I think this idea of using large language models for search is an interesting one. Like you can use it to search through the state space. I think that's what you're saying, right? Yeah.
No, my original idea is to use it for association. Yeah, I think in a way it's the same thing. Yes.
Yeah, you associate to the next state. So in some sense, it's using the large language model.
Help you to retrieve your information.
Yes.
Better, yeah.
But then the information itself may or may not be stored in the large language model. It may be stored in an external table.
Yeah.
The question will then be, how do you evaluate the outputs of your large language models with respect to that external table in a fast way? Because if you want to ground this in like, if let's say your grounding of the large language model is on the grounding in the memory bank, then how do we evaluate the correctness of the LLM in a fast way? Yeah, so this is something that can be looked into. I think maybe there can be an efficient way to like refer the output to the memory bank. Something like, early on I talked about like you have a certain query. Okay, your query over here. You then broadcast this query into some central area where you can go through to all the different memory nodes. And then the memory nodes can then like, the more close you are to a certain memory, the closer you are to that memory, the faster the the faster the reply. And then based on that reply, we can like tell how close we are to that particular memory. So, if you could do something like that, you query based on the LLM's output as a query. And then you query your memory bank. And then your heuristic here would be, the similarity to any entry in the memory bank. Yeah, so actually this can be done in a very quick way if we do it in a very parallel memory system. Yeah, I don't know whether this diagram is obvious to you, but yeah, it basically broadcasts the query to all the memory cells or memory entry. And then each of this like table in the memory is like a separate node or separate agent, and they can process information independently. And then you can just put them back to the central node.
It's a distributed way of doing retrieval.
Yes, correct. So instead of having a central system to store the table, all your entries are distributed and all your memories have like an independent way to reply. Yeah. I mean, I thought of this thing. I don't know whether it's implemented before, but I just thought of this thing because I was trying to make things more parallel. So this is the most parallel I can think of. Yeah, anyway, thanks so much for the input. I think this was a very interesting discussion. I do think that the future will be somewhat like some form of querying of a language model, because you see a lot of things like goals, arbitrary goals, right? You kind of need language to, or rather, it may not be language itself that is the goal. It can be a sub-symbol of language, but language can be a very good proxy to your goals. Like before, like my kid could speak, all right, it's very hard to tell him what to do. All right, so the goals that he probably uses maybe more like those innate one, like you're born with it, like food, water, and then the higher order stuff, it can be difficult to actually quantify those goals. But once you have language, you can then quantify the goals. You can ground it in language. Yeah. So anyway, this is the next part. Yeah. So this arbitrary goals one, again, this might be grounded in language, but it might be another thing also. I'm more tempted to think that language can be sufficient for goals already. Yeah, again, LeCun says that language may not be enough. There are a lot of things that are not expressible by language, like maybe body language, that kind of stuff. But all these things, you can probably still use like a transformer like architecture to model. You probably just need to have
You can have a multimodal
yes. You
large
can use
language model, right?
model
because there's already vision transformer and the audio signal processing. I believe it also can be done in the attention way.
Yeah, so you took the words out of my mouth. Yes, I was about to go to multimodal. So yes, body language or this maybe is visual, Yeah, so
maybe it is already set in motion. We just don't know yet.
yeah. So
I think of this counting.
Right, I think this the development of all these multimodal transformers, all this is good. Then I don't have to train it. Then I can just take the pre-trained model and run it. Yeah, so because this actually ties in quite well with this fast and slow system that I'm envisioning for. And all these advancements elsewhere in like large language models would definitely help the performance of this agent, because it can then take in a lot of different inputs. Yeah, and you can model a lot of goals. Yeah, not just text-based goals. You can model picture-based goals also.
But like I have seen works on actually model sequential decision process with this thing itself. So basically, it's like integrate everything into.
How's the performance for those?
Yeah, that's one thing. There might be some trade-off because maybe next token prediction is not as good to model things like uncertainty.
Okay, so this is the dichotomy between general versus specific. The more general your system, right, the less the less kind of like basically the more general you are, maybe the more inefficient, to actually model your system. Because like if you were to use like large language models to perhaps do mathematics, all right, you may get the answer in the end, but it might actually go through a lot like chain of thought, scratch pad, that kind of stuff. You might need to use a lot of tricks to do it. Whereas if you have a very specific things like a calculator that does it, this actually is very efficient. Okay, but then again, if you do a more general method, you can do more things. So it is again, a trade-off, all right, between like how much inefficiency can you take? All right, if you can take a lot of inefficiency, you can then model with the most general architecture. If not, then we need to split into sub-architectures and model them separately. So I'm thinking for, at least for goals-wise in this system, the goals-wise can be modeled using an LLM vectorized state. Yeah, so you take the vectorized state of the LLM, and this vectorized state, right, because of the way this low memory system works, you need to compare it to the goal. It should be similar to this abstraction part of memory. So it might be the case that you need to sort of like train like a transformer-like architecture to like already learn the vectorized state, and then you use this vectorized state in order to store your memory. So you store in a state that is similar to how the transformer is, but there's a catch, okay? The catch is that you must use the same transformation for states for both memory and the input. Okay, because if you don't use the same transformation, you don't match apples to apples. And there's also a very high chance that your initial steps, right, should be frozen. Okay, if not, your transformation mapping might change. Like as you learn the transformer part, your memory part, unless you share the same architecture, like, okay, let me just draw this. I think this is a very important point. Unless you share the same architecture, like same backbone, so like this, your input, okay? And then you share your, unless you share a common backbone, all right? So your input will go through this, okay? Maybe your memory will also go through like the same kind of backbone, like will get processed in the same way so that you can actually use the hidden states here. So like the memory has a hidden state and the input has a hidden state here. Let's just draw these circles as the hidden state. Yeah, you need to have the same sort of hidden state. Then you can then compare whether or not you reach your goal based on this hidden state here. Then you can then compare like these two. And I guess you can probably have a learnable backbone. So this backbone probably can be learnable, but you need to apply the same backbone for your input and your memory. And yeah, so that's one way to do it. Yeah, but one, I guess you could do this in order to do like comparing between arbitrary goals. Yeah, this is something that is quite interesting to think about, because this idea of like goals and arbitrary goals and like how you store memory to link to your goals, all this is quite interesting. Yeah, because like, for kids below 2 years old, they don't really have memory, not even short-term memory. And this is something that I was thinking about recently. I think it might be because once you are born, this backbone is not trained yet. Yeah, so you don't really have a very stable way to store memories. But once you reach 2 years old, you've already seen most of the world. Then this part here, right, after 2 years old, okay, so this is entirely my theory. Okay, this is not grounded in any scientific thing. Maybe after 2 years old, this is fixed. Yeah, so like maybe like if you haven't seen something when you are younger, like you may not be able to differentiate them as easily next time. Yeah, like the backbone has been fixed for your memory storage. Yeah, but of course it may be learnable throughout your entire life. Yeah, I'm just thinking that in order to like store memory effectively, it's better to store memory not in the input space. You know why? Because the input space here is huge. Okay, the input space like for vision, for audio, this actually input space is huge. What we want to do is we want to store memory in this space here. This is limited and constrained. All right, and this is actually better to store memory because it takes less information to store compared to your input space. So my theory is that after 2 years old or 3 years old, we stop forming this backbone, and then we can store your memories in the abstract space, which will be used throughout your entire life. Yeah, I don't know what you think about this. Yeah, this is just a theory that I've been thinking of recently. Yeah, so this might explain why we don't remember stuff below 2 years old. Yeah, we haven't been able to form the right backbone for your memory yet, for our memory yet. Yeah. Okay, yeah. So I think that was quite a like interesting thought. Yeah, so this one we already talked about it. How to determine sub goals is something like secant. Again, is somewhat like large language models. Yeah, unfortunately, because these goals can be very arbitrary, we need a very expressive architecture to store it, and we incur some inefficiency in training. No choice. So I think like a transformer-based architecture or large language model might still be the best architecture right now to do this goal and sub-goal modeling. Yeah. Okay, actually, that's more or less the end for today. Yeah, I think exceeded 2 hours by a bit.
Sorry,
yeah.
I have one last comment.
Oh, yeah, sure.
Before we go. So regarding your one of your comment previously, which is you think that we don't need logic to think through when we do some things, right?
Yeah.
You just directly immediately make the decision, right? You don't go through logic. Actually, I have another interpretation on this phenomenon, because I believe logic is grounded in and shaped by past experiences. If you think about it, a lot of things you think make sense, right? It comes from your past experiences, and you accept this experience in a way that logic is embedded in our brain as a form of muscle memory. And you don't really need to explicitly think about it when you make decision. It's already part of your I'm not sure whether it's the correct word to use, subconscious. That's why when you make decision, right, directly make decision. But if you after that you think about it, I realize, oh, why I make this decision? Because I'm so used to think in this way. So that's my theory on that.
Yeah, maybe your definition of logic is different from the definition I was thinking of. Yours is look more like past experience, right? Your logic here is like what you're used to, what you have seen before.
No, even for the formal logic, or like logic in mathematics or rational thinking, your rationality is also part of the muscle memory. So you don't need to explicitly go through the thought process again, because you have done it in the past.
But what if you have done something irrational in the past?
Like
rationality is actually more like a societal thing, right? Like you are rational because like you do something that.
No, yeah. On that, I also have one explanation, because a lot of things perceived as irrational, it's actually rational from another perspective. So
yeah, it might be rational for you. Like maybe you want money, so you rob the bank. It's very rational for you. But it's irrational, maybe someone else viewing you because like, oh, this guy can work. He could actually get the money. Why did he rob the bank? That kind of stuff.
Yeah, but come back to the discussion on your immediate action. So sometimes maybe you think your immediate action is not rational, but actually it's possible to find the interpretation to rationalize it.
Yeah, actually a lot of things can be back reason. Like why you do a certain action, right? Can be back reason in many, many ways that sound.
So yeah, so basically the reason we don't need to think again, because like I'm not sure, because I'm not familiar with the neuroscience, but I feels like it's like the part of the circuit in your brain is already wired in this way. So it's easier to think in this way. That's why you don't even think about it, because the thinking process, I think you mentioned before, right? When you think very hard, you consume a lot of energy, right?
Yeah.
I think that's because you are forming this connection in your brain. That's why it consumes more energy. But when you already form this circuitry in your brain, you don't need to go through that process again, which means that you don't need to explicitly think about it, think through the process, and you just do it almost subconsciously.
Oh, okay. I know what you're talking about.
Yeah.
You're talking about, I think it's very similar to like sequence of trajectory, like that you have a sequence of like in rational thought, like one links to another, right? You have a chain of reasons already, you already learn.
Yeah.
And then to access this chain of reason, you don't have to search anymore. You can just access it like that.
Yes, because not even search. Sometimes when you think through, if you have encountered some question, now you encounter different think through it, you need to really build up this connection. So of course, it's easier to just flow through this existing connection rather than
Actually, what you say about rational thinking has led me to think about something for this sequence of trajectories. Like, as long as your current trajectory here, like sort of matches like us, so maybe it might be still like useful to store things in terms of like goals, right? You can actually, if you can match over here, you can then reuse the entire sequence of trajectories.
Yes, yeah. Because it's much easier, because you already formed this trajectory. So that becomes the part where you can almost call this logic.
Okay, you must be careful here, right? Because not all sequences are deemed logical. Logic is more or less a human imposed construct. So, you know, although things might flow to you, but it may not be a logical flow, you see?
No, I'm just saying that this logic is the thing that you don't need to take time to think through.
But I don't think so, you know, because like in order to use logic to evaluate things, you kind of need to use the logical thinking, which incurs effort. It's not a natural way of thinking.
Yes,
Like,
because this logical thinking is trying to evaluate whether this path is
right, no,
correct.
even if I already experienced that path before, I kind of still need to use effort to rethink of the logic behind that path again. Like,
Yeah,
even
but
if I've
because
done it,
this thinking is not using that existing path, you see, the evaluation use some other things. It's not the same circuitry. Evaluation is an independent process of forming this trajectory. To form this, after you form this, you take action, you form this trajectory. But you evaluate, you use some other trajectory. Yeah.
okay, I mean, this is open to debate. I think
I mean, it's just my personal.
I do not think that
postulate.
logic can be effortless. That's my point. I think you still need to use some effort, even if you've encountered it a lot of times. I still think you need to use effort or
Then I
rationale.
give you one more example. When you solve some complex differential equation or integration, right? Do you actually still explicitly think about the most basic operations such as 1 + 1 = 2 or some rule like chain rule or whatever you think before? If you do very complex tasks, those things you do it subconsciously, right? You don't explicitly think about it, but that's logic.
Okay, I think, I mean, William also mentioned one thing in the chat, and I also agree. Like the way you're talking about logic here could be something like an intuition about what to do.
Yeah, so it's in a way it's more general, but come back to my specific example, that's definitely logic because it's mathematical. It's mathematics. You learn it
But you
before,
can also
you
treat
think
it
without
as
thinking about
a
it.
sequence finding problem to solve a math problem.
What?
It could also be interpreted as a sequence finding problem.
Care to elaborate?
Also, like to do differentiation integration is like different actions that you take in order to reach a goal, right? Which is to solve the problem. The way of logical thinking that you describe can also be reframed as a goal-seeking problem, right?
Right, but why you feel it's challenging? Why you need to take time to think about it?
Because it's a set of formal rules, you see. In order to do search-based problems, like goal finding, you necessarily like need to sort of like evaluate different branches. Not all branches, but some branches.
And why when you actually work through the problem, you solve the sub problem, you don't find it difficult. It doesn't take much time to solve those sub problems.
Actually, that might be because like that's why I say here like you might already store this sequence of
exactly. You already found the muscle memory. You have the circuitry.
Yeah, this is like the solve the sub problem, right? You already know how to solve the sub problem. You can just access it.
Yeah, exactly. So like my explanation kind of subsume like the why you like to explain why you think sometimes you need to think through, but sometimes for some simple problem you don't need to think through. Right?
Okay, now let me just tickle your mind a bit. Could this be related to hierarchical planning? Like over here is like solving by differentiation, right? And you already know that maybe this series of steps solve it. So what this could be doing is that you have strengthened your like you strengthen the bottom layer. Yeah. So the more you strengthen like your bottom layer, like the more you do, this part is very obvious to you now. And then when you like plan at this level here, immediately like this sequence appears to you. So it's not exactly effortless, but because of the way you have like accessed this thing many times, you sort of like learn how to get the actions like very easily.
Because you need to gather those sub actions, right? Because at this level, it is not immediately clear how do you organize in certain way. So that's not trivial. That's why it takes efforts to do that. But for each individual subtask, which you already know how to solve, it doesn't take effort anymore, right?
So this could be like a subtask, and then the effort that you take maybe is like in terms of effort to find the goal. And the effort to find the goal, if your memory model is updated to the most relevant, which basically because you have done this a lot of times, your amount of effort taken to solve this would be much faster, right? I mean, much lesser because
but my point is, when you first solve this the problem, you still need to take effort. But when you already solve it, it does not need to take as much effort.
yeah. So maybe if you view it like the fast and slow architecture, number one, your memory is updated to the most relevant like memory, and then you can just retrieve it like almost immediately. And number two, maybe your fast goal directed neural network is trained very well also. So you actually like get the right first action much faster.
So okay, then come back to the example you gave in the first place. So sometimes our first reaction can be rational, sometimes can be not rational, right? But when it's rational, it's because we already built in this existing trajectory which is rational. But because this thing can be not rational, can be irrational. That's why our first reaction sometimes can also be irrational.
Understand. I actually, what you have told me, right? I thought of something new. Okay, so you listen to this. This one, I just thought of it because of what you just told me. This one can actually be used to bias your action selection in this memory, right? Because like you have a fast neural network that can be trained to be more efficient the more you do. So like, for example, state one, I know that I should take the action up most of the time. I prioritize the action up according to the percentage of probability of this action. So you can use the fast network to bias memory retrieval.
Yeah, I can see where the reasoning comes from.
Oh wow. Hey, if this works, right, your name can be in the paper, you know. Oh wow. I didn't think of this, but it does look like this can be done. And this would perhaps be easier to implement than using a transformer.
So
because
you are saying that some subgoal we know that it's more likely to occur in solving some tasks. You just bias towards those subgoal first.
yeah, because your subgoal modeling can be done here also. This goal can be your subgoal.
Right.
Yeah, in fact, this can also be done in a hierarchical manner. So like after you take this action, this is layer one. You can then do layer two of this. So the memory for layer two will be the higher order level memory. Like not just the input memory, it will be like if your input memory is moving your leg left, moving your leg right, your layer two will be moving forward. Then layer three will be like point A to point B. You know, you have different levels of planning.
Okay, I need to have some time to think about it.
Yeah, each level of planning has different memories that are specific to the abstraction layer.
Okay.
So yeah, but okay, let's don't talk about the hierarchical planning because that's something that is very exciting. But we just take a look at this single level planning. You could use your fast neural network to bias the memory retrieval to select paths that are more relevant, right? Because you already know.
If you know you have a prior over what the most primitive action is more likely to be taken.
Yeah, actually, this way of using the fast neural network to bias your memory retrieval might make your memory be more efficient. Like the sequence be more efficient. This definitely can help.
I actually make a lot of sense because you think I can think of another example. For example, you have a very hard math problem or like proof problem to solve, right? You always like think of you have some intuition of like the first thing comes to your mind is those tricks you think it mostly like to be useful, right? To be helpful. That can be think of as all these
Yeah.
right?
It makes sense.
You get what I mean, right?
It makes sense. So I can buy your idea of this. The more you think about something, the faster you get it done. And I think what I just talked about, like using the fast neural network to bias the retrieval, can achieve the outcome. Yeah.
Right.
Interesting.
So in a way, this is like an implementation of that.
Yeah. No, in fact, this is a very easy implementation. Yeah, and this can actually it might actually benefit the performance. I'll go and try it out. We see how it goes. Yeah, but thanks for the suggestion. Okay, I mean you didn't exactly suggest it, but the cases that you described, made me think of it. Yeah.
Okay.
So yeah, thanks for that.
Maybe we can discuss offline also.
Yeah, definitely. I mean, if you like to help to improve this model, we can do it together. Yeah. Okay. But for the rest, any other concluding remarks? I think this discussion today has been quite interesting. Yeah. And this definitely, if we can get this right, this can be the basis of the fast learning agents in the future. Yeah, we don't really have to use current RL methods. We can use this method for problems that don't require optimality. Like for example, stuff that is not like winning a board game. Board games are actually games that require optimality. Yeah, that's why humans find it challenging. Yeah, but for those cases that we don't need this, actually, this system would be very useful, like the fast and slow system. And like how exactly to model the fast, how to model the slow, these are all open questions. How to model the goal, this is also an open question. But I think the rough idea of using memory, of using some form of good retrieval and storage, I think those are very important questions to answer. Yeah. So yeah, I will probably end here. Any last points before we call it a day? Okay, thanks for coming. Yep. And thanks for the discussion. Yeah, I'll be stopping the recording now.